In this lecture, we're going to start understanding chemical bonding, the different types of chemical bonding when it comes to chemistry, and the entire concept of chemical bonding revolves around stability. Now, I'll first give you the concept of why different atoms bond. The reason why, there are different types of bonding. There's ionic bonding, there's covalent bonding, there's metallic bonding, etc. So the reason why atoms bond is atoms bond because it makes them more stable. Now, I'm over and over again I'm using this concept of stability and becoming stable. And what do we understand by stable? If something is stable, the basic idea of stability is if something is stable, it resists change. It's going to resist change. In physical terms, it means that it's going to have very less potential energy. So in physics, if you're familiar with the term potential energy, stable means that it has low potential energy, and I can simplify that. What potential energy means, or low potential energy means, that it has low potential to do any type of work. It's going to resist change. It's not going to change. For example, I have a pin. Let's say I have a pin in my hand, and this is the ground, and there are two states. This is my ground. There are two states that the pin can actually I can put the pin on the ground. One is I can put it, let's say this here is my pin, and I've placed it on its edge. And the other way that I can put the pin on the ground is I can put it flat on the ground. Which state is more stable? This one is stable. The reason is that it won't do any work. It has no potential to do any work. It's going to resist change. It's not going to change on its own. It's going to stay flat on the ground. Whereas this one is unstable. If I leave it there, there's a very high probability that it can topple over, it can fall over. So there's a lot of potential for it to do work. Now, if you look at your universe, around your universe, if you look at anything, things in general, you can take things as planets, things can be atoms, things can be molecules. Now, things have a desire to become more stable. They would never remain unstable. They're going to, if they have a lot of potential energy, for example, this pin in its upright position is unstable. It's going to fall on its side one time or the other. It's all, there's a lot of energy in it. It can't do work. It's going to fall to one side, and it's going to become stable eventually. So things have a desire to become more stable. Now, if you've understood the concept of stability and the fact that things have a desire to become more stable, I've drawn two atoms. One is lithium. It's 3 and 7, 3 protons, 4 neutrons, and there are 3 electrons. And I have a fluorine atom with 9 protons. The atomic number is 9, and 19 is the atomic mass. So 9 protons, 10 neutrons, and then 9 electrons. So I've drawn the atomic structures of both atoms, and now you've got to guess whether this state is stable or not. Now, if you look carefully, what you're going to see is that lithium has 3 protons in its nucleus. So the positive charge on the nucleus is the positive charge on the nucleus is lesser, and if you look over here, fluorine has 9 protons. Now 9 protons would have a lot of positive charge, so the positive charge on nucleus is relatively large. It's larger compared to lithium. Now what's going to happen is that this nucleus is going to attract electrons very strongly, and if it ends up attracting electrons very strongly, if you look at this electron over here, this particular electron is very far from the lithium nucleus, which is over here. It's in the outer shell, whereas these 9 protons are going to attract this electron towards the fluorine atom. So since there is going to be change happening in this system, so this is an unstable state. And when you see what happens is that lithium, because it has 3 protons, the positive charge is not very high, it's going to lose this electron, and that electron is going to end up with fluorine. So a more stable electronic configuration when these two atoms are together would be, let's redraw that, lithium would be, it's going to have 3 protons and 4 neutrons, and you're going to have you're going to have 2 electrons in the outer shell, and lithium is going to lose this electron, which is eventually going to end up with fluorine. So lithium would eventually lose that electron, and when it loses one electron, lithium would have a charge of +1. What happens to fluorine, on the other hand, is that the nucleus of fluorine is going to have 9 protons, 10 neutrons, and the first shell is going to have a total of 2 electrons, and the second shell, which was previously having it was having 7 electrons, but one of the electrons is going to go from the lithium to the fluorine atom because the proton number is higher. So that electron ends up with fluorine, and since it's gaining 1 electron, the charge on a fluorine ion would now be -1. So you get a fluorine -1 ion, and you have a lithium +1 ion. Now compared to the previous electronic configuration, this is more stable. It's going to resist change now. These 2 electrons are now firmly under the control of lithium. The outer electron is lost because lithium it had only 3 protons, so 3 protons were not able to attract the outer electron that strongly. That electron went to fluorine because 9 protons were strongly attracting electrons, so that electron ended up with fluorine, and this is a more stable electronic configuration compared to the previous electronic configuration where lithium had 3 electrons and fluorine had 9 electrons. Fluorine having 10 electrons and lithium having 2 electrons is now more stable, and this applies to all the atoms. So a general rule is that atoms or ions having complete outer shells have a more stable electronic configuration. we've already discussed what makes atoms stable. Complete outer shells. Whenever something has complete outer shells, that electronic configuration is stable. So a stable electronic configuration would have a complete outer shell. And we'll go through the periodic table first. Let's say the periodic table, if you have a periodic table, it's the columns are called groups. So you have group 1, you have group 2, you have group 3, then you have group 4 and group 5, group 6, group 7, and then there is group 0, which is called the noble gas. They're called the noble gases. So in group 1 you have you have lithium, which is 3 and 7, and you have sodium, which is 11 and 23. Now let's discuss group 1 first and see how can we make them stable. So we have group 1, we have lithium, and let's draw the electronic configuration of lithium, which is lithium is 3 and 7. So I'll draw the electronic configuration of lithium. Lithium is going to have a nucleus, and that nucleus would have 3 protons, and it's going to have 4 neutrons. 7 minus 3 is 4, and it is going to have 3 electrons. So the first shell, the K shell, has 2 electrons. That's maximum it can accommodate. And then you have it has 3 electrons, so there's going to be 1 electron in lithium's outer shell. Now lithium is unstable. As you can see, it does not have a complete outer shell. To become stable, lithium would need to do 2 things. To achieve stability, it can either lose its 1 electron, or the outer shell. To complete the outer shell, if it loses this electron, then this shell is gone and you have a complete inner shell, which then becomes the outer shell. So losing 1 electron would make it stable. On the other hand, it needs 7 electrons to complete its outer shell. So the other thing it can do is it can gain 7 electrons, and those 7 electrons would make it stable. But the easier thing for lithium to do is lose 1 electron. So what happens is lithium ends up losing this 1 electron. So more stable electronic configuration for lithium would be, it's going to have 3 protons, 4 neutrons, and you're going to have 2 electrons in the outer shell. Now this outer electron is lost. When it is lost, that means whenever something loses an electron, there would be lesser negative charge, so the positive charge increases, and when it loses 1 electron, the positive charge would be +1. So we draw square brackets and +1 is written on top of it. So this is a stable lithium ion, so it's Li +1. So that's lithium. Similarly, we can do exactly another group 1 element is sodium, which is 11 and 23, and I'm going to quickly draw the atom of sodium. So sodium atom would have, it's going to have 11 protons, and it's going to have 23 minus 11, that's 12 neutrons. So it has 11 protons and 12 neutrons. And the number of electrons in this would be 11 electrons, so there would be 2 in the inner shell. Then we draw the second shell, which is going to have 8 electrons. These electrons are drawn in pairs, and that's a total of 10 electrons. It has 1 electron left. So it has 1 electron in its outer shell, and this again is an unstable electronic configuration. To become stable, again what sodium can do is it can either lose 1 electron, it can lose its outer electron, so the new outer shell would be this inner shell, the second shell, and it would have a complete outer shell, or it can gain 7 electrons to complete the outer shell. But what sodium does is it's easier to lose 1 electron. So what sodium does is it eventually ends up losing 1 electron. So let's redraw this. You have 11 protons and you have 12 neutrons. So there are 2 electrons in the inner shell. There would be 8 electrons in the second shell, which is the L shell, and sodium is going to lose this outer electron. So when it loses 1 electron, it's going to get a +1 charge. So this is a stable sodium ion. Now if you have been observing carefully, lithium was in group 1. Lithium was in group 1 and it lost 1 electron and it eventually ended up forming lithium +1. So was sodium in group 1, and sodium lost 1 electron as well, and it ended up forming Na +1, which was more stable. If you keep on going down group 1, let's talk about potassium. I'm going to write potassium over here. Potassium was 19 and 39. It had 19 electrons, and the way 19 electrons are arranged, without drawing the structures now, there would be 2 electrons in the inner shell, 8 electrons in the second shell, 8 electrons in the third shell, and there would be 1 electron in the last shell. And to complete the outer shells, what potassium could do is it can either gain 7 electrons to make 8, or it can get rid of this 1 electron. And what it does is it eventually ends up losing 1 electron. So this K would then become K +1. So K, or potassium, would also lose 1 electron, and it's going to form K +1. So the general trend is that group 1 is always going to form +1 ion, and it's always going to lose 1 electron, become more stable. And we can go to group 2 now and see whether the same trend is followed by group 2 elements. Let's look at the group 2 elements in the periodic table. Group 2, the first one is beryllium. Beryllium is 4 and 9, and it has a total of 4 electrons. So the electronic configuration is going to be, there would be 2 electrons in the inner shell, and there would be 2 electrons in the outer shell. And this electronic configuration is unstable. To become stable, what it can do is it can either lose 2 electrons, get rid of these 2 electrons, or it can gain 6 electrons. But there should be 6 electrons. If it gains 6 electrons, there would be 8 electrons. It would have a complete outer shell. So it's easier to lose 2 electrons instead of gaining 6 electrons. So it ends up losing 2 electrons. And when it loses 2 electrons, beryllium would then become, it would have a charge of +2, and there would only be a total of 2 electrons in the inner shell. So beryllium is going to form a +2 ion. And so will other elements in group 2 form +2 ions? Beryllium, we have beryllium, then we have magnesium. Magnesium is 12 and 24. That's the second element in group 2. So if you have magnesium, magnesium has a total of 12 electrons, and the electronic configuration would be 2, 8 and 2. So it's the same case, the electronic configuration is unstable. It does not have a complete outer shell. There should be 8 electrons over here. What it can do is it can either lose 2 electrons or it can gain 6 electrons. It's easier to lose 2 electrons. It's getting rid of these 2 electrons. When it gets rid of these 2 electrons, Mg would then have a charge of +2. And if you do it on your own, you'll see that group 2 elements always have a charge of +2. We can look at calcium, which is 20 and 40. So calcium has 20 electrons. The electronic configuration for calcium is going to be 2, 8 in the second, 8 in the third, and 2 in the fourth shell. And it's going to lose these 2 electrons. So calcium would have a stable electronic configuration when it loses 2 electrons. So +2 would be the ion which would be stable. So calcium would also form a +2 ion. So group 2 elements form +2 ions, and that's a general trend. Group 1 ions form +1. Similarly, we can check this for group 3 elements. In group 3, we can find out the electronic configuration for boron, which is, now boron is 5 and 9. So it has 5 electrons. The electronic configuration for boron is going to be 2 electrons in inner shell, and there would be 3 electrons in the outer shell. So to become stable, it needs a complete outer shell. So it can either gain 5 electrons, so that there would be 8 electrons in the outer shell, or what it can do is it can lose these 3 electrons to become stable. And it's easier to lose electrons, so boron ends up losing 3 electrons. When boron loses 3 electrons, it's going to form boron +3 ion would be formed to become stable. Another group 3 element is aluminium, the one that we previously just did, 13 and 27. It has a proton number of 13. That means it's a neutral atom is going to have 13 electrons, and 13 electrons would have an arrangement of 2 in the inner shell. There would be 8 in the outer shell, and there would be 3 in the last shell. And to become stable, it's again going to, it can either gain 5 electrons, or it can lose 3 electrons, and it's easier for it to lose 3 electrons. So it's going to lose 3 electrons as well. So a stable electronic configuration for aluminium would be 2 and 8, and therefore aluminium would have a charge of +3. It's going to form a +3 ion. So remember, group 3, the general trend is that group 3 elements generally form +3 ions. We can move to group 4 now. So in group 4, we have, let's talk about carbon. We have carbon, which is 6 and 12. Now the problem with carbon is that the electronic configuration has 6 electrons. The electronic configuration for carbon is 2 and 4. There are 2 in the inner shell and 4 electrons in the outer shell. And to have a stable electronic configuration, carbon either needs to gain 4 electrons, or it needs to lose 4 electrons. Now remember, the gaining 1 electron is very easy, or losing 1 electron is relatively easy, but gaining 4 electrons or losing 4 electrons, it becomes difficult. So it becomes difficult. So what happens with group 4 is that they generally don't have a tendency to form ions. So they generally don't form ions. But if they were to form ions, they would do both. Carbon could either be +4, it could be -4. It's equally possible, but they generally don't form ions. We can then move on to group 5, and when we talk about group 5, let's say group 5. Now in group 5 you have let's say nitrogen is in group 5. It has its atomic number is 7 and its atomic mass is 14, so it has 7 electrons. There are a total of 7 electrons, and the way these electrons would be arranged, there would be 2 electrons in the inner shell and there would be 5 electrons in the outer shell. Now for nitrogen to become stable, it needs a complete outer shell. It can either gain 3 electrons, so you have 8 electrons in the outer shell, or it can lose these 5 electrons, so the inner shell becomes the outer shell and becomes stable. So it's easier to gain 3 electrons in nitrogen's case. So nitrogen would end up, there would be, instead of 5 electrons, there would be 8 electrons in its outer shell. So it's going to gain 3 electrons. When it gains 3 electrons, nitrogen would then have a charge of -3. So group 5 is going to form -3 ions. We can look at another one. We can talk about phosphorus, which is 15 and 31. And for phosphorus, it has 15 electrons. The electronic configuration for phosphorus is it's 2 electrons in the inner shell, 8 in the second shell, and you are left with 5. So there are 5 electrons in the outermost shell, and again it can either gain 3 electrons, it can lose 5. So it's going to gain 3 electrons. So 3 electrons would be gained, and when phosphorus gains 3 electrons, phosphorus would also have a charge of -3. So group 5 has a general trend of forming -3 ion. Now let's move on to group 6. In group 6 you have let's say we have oxygen, which is 8 and 16. A neutral atom of oxygen is going to have a total of 8 electrons, and those 8 electrons, the arrangement of those 8 electrons would be, it's going to have 2 electrons in the inner shell and there would be 6 electrons in the outer shell. For oxygen to become stable, it needs a complete outer shell, so it can either gain 2 electrons or it can lose a total of 6 electrons. So it's easier for it to gain 2 electrons to become stable, and it ends up gaining 2 electrons. So there would be 2 electrons that would be gained by oxygen. These 2 electrons would be gained, and when it gains 2 electrons, oxygen would then have a charge of -2 on it. So group 6 have a tendency to form -2 ions. Let's take another element of group 6. We have sulfur in group 6, which is 16 and 32, which means it has 16 electrons, and the electronic configuration would be 2 electrons in the inner shell, there would be 8 electrons in the second shell, and you're left with 6 electrons again in the outermost shell. So again, it can either gain 2 electrons or it can lose a total of 6 electrons. It's easier for it to gain 2 electrons, so there would be 2 electrons gained by sulfur, and you'll have a total of for a stable sulfur, it will eventually end up with 18 electrons. When it gains 2 electrons, the charge on sulfur would then become -2, so it's 16, 32, and sulfur would have a charge of -2. And finally we can move on to group 7. We'll start off with fluorine. Fluorine is 9 and 19, which means it has a total of 9 electrons. The electronic configuration for fluorine would be, it's going to be 2 electrons in the inner shell and there would be 7 electrons in the outer shell. Now it has 7 electrons in the outer shell, which means it can either gain 1 electron, it just needs 1 electron to complete its outer shell, or it can lose a total of 7 electrons. So it's easier for it to gain 1 electron, so it's going to end up gaining 1 electron, and there would be a total of 10 electrons eventually in a stable fluoride ion. So fluorine would then have a charge of -1 because it's gaining 1 electron, and it's going to have a charge of -1. Let's look at another element of group 7, which is Cl, which is 17, and one of the isotopes of chlorine is 17 and 35. So for chlorine, it has a total of 17 electrons. The electronic configuration is 2 electrons in the inner shell. There would be 8 electrons in the second shell, and there would be again 7 electrons in the last shell. So again, it needs to either gain 1 electron or can end up losing 7 electrons. It's easier for it to gain 1 electron, so it ends up gaining 1 electron, and when it gains the electron, Cl would then have a charge of -1. And if you can also draw the structures for group 0 elements, and you'll find out that they don't they already have complete outer shells, so they won't gain or lose electrons. So to sum this up, what we discussed previously was that if you look at the periodic table, you'll have groups. You'll have group 1, you'll have group 2, then you'll have group 3, group 4, and group 5, group 6, group 7, and you'll have group 0. Now what we've learned so far about these groups is that let's talk about group 1 first. It's going to have 1 valence electron. Any element in group 1 is going to have 1 valence electron. That means it's going to have just 1 electron in its outer shell. Group 2 is always going to have any element in group 2 has 2 valence electrons. So the outer shell in group 2 of any element in group 2 is going to have 2 valence electrons. Similarly, if you look at group 3 is going to have a total of 3 valence electrons. Group 4 have 4 valence electrons, and then you have group 5, which has 5 electrons. Group 6 has 6 valence electrons. Group 7 has